paper, two books, one in numerical linear, which was his main field, and more recently a book on control systems. He has received lots of distinguished prizes. He's IIIO Fellow, and Simultaneous Award, Academy of Knowledge in Russia. And yeah, we'll stop there, but otherwise you can check on his webpage. And today he's going to tell us about, well, the title is this. It's about active control of vibration, active vibration control. Buildings, aircraft. He has been collaborating with Boeing company and also with warfare research. You know, from Mathematica, he developed a couple of toolboxes for numerical linear algebra and optimal control. And there are also freely available toolboxes for MATLAB. So if you have any numerical linear algebra, just talk to Biswa. Okay.
Okay, so how do I do that?
Oh, it's right. So you can just use the
Oh, up and down, right?
or to the sides. Any of those.
Okay. Buenos días. Buen día. Good morning. I think everybody here speaks better English than I do, even. So I don't have to speak in Spanish or Portuguese or Portuguese or Portuguese. I'm very pleased to be here. And I'm honored and very much thankful to my longtime friend, Professor Roberto Cominotti, and colleagues Rodrigo and others for inviting me here to this beautiful campus. It's one of the most wonderful campuses I've ever visited. I've been around the world, but this is indeed splendid. I like it. And I hope you will invite me again to come here. No, it's really beautiful.
We invite you back today, it's not cloudy.
Yeah, that's right. I'll come during the summertime.
Yeah. Winter time we have snow.
Right, but it's really nice. It's beautiful. Okay, my talk here, as you can see from the title, is sort of interdisciplinary, blending mathematics, computations, optimization techniques, and electrical and mechanical engineering. And who gives an interdisciplinary talk like this? People who don't have any expertise in any of these areas. And I was one of them. Anyway, so let me start. We are quite a few minutes late anyway. So there are several collaborators of mine all over the world, so I will not go over their names now because it's too long. Let me start with this motivating example. This is the Millennium Bridge on the River Thames in London, England. An interesting fact about this bridge, that this bridge was closed within 2 days of its inauguration. What happened? On the day of inauguration, several hundreds of people came all the time to see the bridge, and the bridge started wobbling. It was not equipped to handle such a big load. And the smart engineer of the bridge, he immediately closed the bridge. And then, after spending few millions of British pounds, the bridge was, the problems were solved temporarily, and the bridge started running all over again. Now, though there are some differences of opinion, but most experts believe that it was caused by resonance, and we all know what resonance is. Resonance, sometimes gives dangerous vibrations to structures like buildings, bridges, highways, aeroplanes, spacecrafts and other vibrating structures, causing unrepairable damages sometimes, even the loss of human lives. We know all know that. There are actually this talk has been designed for mostly for students, but I don't see many students here. It's not for the experts. So okay, so the first part of my talk is on active vibration control. That's what I'm talking about. Now, you all know there are other infamous examples of vibration, dangerous vibration caused by resonance, like the fall of Tacoma Bridge. You all know about that. And I don't know whether, I am sure some of you know this story. There's an interesting story behind this bridge, behind the fall of this bridge. The principal architect of this bridge was a professor of civil engineering at the University of Washington in Seattle. He thought he did all his mathematical computations so well that nothing could go wrong. So he even asked the state of Washington not to buy an insurance on the bridge. But that he was wrong. The day came when that gusty wind was blowing on the bridge, and the bridge started wobbling. Seeing this overconfident professor, he ran to the bridge and stood there on his feet to prove to the whole world that his mathematics cannot go wrong. Ultimately, his life was saved by a police helicopter. So anyway, so these are some of the infamous examples of resonance. So the question is that how do you control such a dangerous vibration in a structure? The traditional way, and actually the more widely used practical, just the damping in a structure. As we all know that every structure, like building, bridges, highways, every structure is composed of three materials: mass, stiffness, and damping. And damping is something cannot very accurately measured. And that's why this kind of vibration is caused. So the traditional approach is to adjust the damping in such a way that the vibration stops. But this approach has some limitations, though it's widely used in practice because it's very economic in nature. But it has some limitations. Limitations are that with this approach, you can control the vibration only locally, not globally. And also it's ad hoc in nature. And it's not, there is no sound mathematical basis of this type of approach. On the other hand, there is something called now active vibration control approach. And this is more scientific in nature, but it's not easy to build a structure with active vibration control. It's quite expensive and very complicated. But there have been some high-rise buildings in Japan and other Asian countries, some bridges. You know that famous twin tower in Malaysia. You know that had active controllers. Some of these structures have been built with active controllers. In Japan is very common because Japan is prone to earthquake. And as a matter of fact, I have a very strange experience in Japan. I was sleeping in a high-rise hotel on the 28th floor. At 3 o'clock in the morning, I got up and found that the whole building is vibrating. And I was so scared, I just got up and didn't know what to do. Before I started doing something about it, it stopped. And my host was a control guru in Japan, actually. You know, he's very famous and very well respected in Japan. He called me and said, "Biswa, are you scared?" I said, I'm a little scared, but He said, don't worry, your type of mathematics is working on this building. So that building had active controller. Now, what is the mechanism of active controller, active control? Well, the mechanism is very simple. Mechanism is that as soon as a building experiences some dangerous vibrations, those vibrations are measured by sensors and immediately sent to a central computer where the amount of force needed to absorb the vibration, to control the vibration, is computed in real time and immediately sent to the structure by means of actuators. So this is the whole concept, very simple. However, the most difficult, important part is how do you compute those active control force needed to control the vibrations in real time, if the algorithm has to be as fast as possible. Okay, so that's the most important part and most difficult part, and that's where my talk will be a little bit about it.
I'm going to be honest here. What is passive damping?
Because
Well, what is it? I don't know.
why the word passive?
Yeah, the damping. No, damping. I don't even know what is damping.
Damping is.
Absorb its vibration.
Amortiguación.
Okay.
Oh yeah.
Okay, so okay.
Okay.
Sorry.
Okay. All right. So so let me tell you now that where that part, my talk is actually the first part of my talk is centered on that part, how to do that. Now, vibrating structures are distributed parameter systems, meaning that real mathematical model is a set of nonlinear partial differential equations with boundary conditions on some Hilbert spaces. So these are all theoretical. Okay, in practice, such systems are discretized into a finite element model by using finite element techniques, giving a second order differential equations of this form. Okay, and the engineers call it finite element model because this model is generated by using techniques of finite element techniques. Now, in this equation, M stands for mass, C stands for damping, and K stands for the stiffness. These are three matrices, and suppose each of them is n by n, and x double t, x dot t, x t, respectively, the displacement, velocity, and the accelerations. Okay. Now, this type of systems are governed, the dynamics of this type of systems are governed by the eigenvalues and eigenvectors, which in engineering literature are called the natural frequencies and the mode sets of a special type of eigenvalue problem called quadratic eigenvalue problem. Quadratic eigenvalue problem is an eigenvalue problem of this type, and this matrix P lambda, I'm sorry, there's an X missing on the left hand side. This matrix P lambda, which is lambda square M plus lambda C plus K, is called the matrix pencil. Now, the quadratic eigenvalue problem is the eigenvalue problem associated with three matrices M, C, and K. It's not very widely known. It is, you can see that the most commonly used eigenvalue problem is the standard eigenvalue problem of one single matrix, X equal to lambda X. Then there is a generalization of this eigenvalue problem, which is called a generalized eigenvalue problem. It's a problem of two matrices, B and C, Ax equal to lambda Bxc. And this is the more general one, quadratic one. Of course, you can generalize further, but this is what we need now. Now, this as I said, this problem is not very widely discussed in the literature because this problem is a quadratic problem, it's difficult to solve. Now, if M, C, and K are n by n, and M is a non-singular matrix, then that eigenvalue, the pencil P lambda, has 2n eigenvalues and 2n eigenvectors. As I said, it's very difficult to solve numerically, impossible to compute all the eigenvalues and eigenvectors from the problem is large and sparse because of the non-linearity, nature of the problem. Okay. Well, I'll come to that later. you can always, theoretically, you can always convert that problem, the quadratic problem, to a standard eigenvalue problem of 2n by 2n matrix. But this is in theory. In practice, if you do that, you lose all the structures of the problem, like the matrices M, C, and K. In practice, have some very special structures. They are symmetric. M is positive definite, K is positive semi-definite. They are banded, sparse. All this nice structure which should be exploited in a computational setting will be completely destroyed if you do that. So the thing is, the challenge is to solve the problem in quadratic setting itself, and that's where the difficulty comes. Okay, and actually, in many attempts, the state-of-the-art technique, like it's a projection technique, where you project the problem to a smaller subspace, and then you solve the problem there and get some approximate eigenvalue and eigenvector. This type of projection technique, as you know, can compute only few eigenvalues and eigenvectors. Okay, and normally they compute the extremal ones. So that's the state of the art. But as you can see that for our purpose, yes.
When you say n is large,
Very large is because they come from finite element techniques, so they could be of order few billions. But in practice, one cannot handle that type of problem. So it could be very large, depending upon what structure you are building. Okay, there is a structure, very high-rise football stadium was being built in Calgary, Canada, and they just could not handle the problem. So they came to the Boeing engineers, not engineers, Boeing mathematicians, to seek their help. And the team of Boeing mathematicians went to help them. And they developed a package. That time, nobody ever thought how to solve such a big problem. The Boeing engineers, after a few years of research, they found some techniques to handle some big problems, only to compute few eigenvalues and eigenvectors. Okay. So that's the, it's very hard to believe, but this is what it is.
Can I ask a question?
Yes, sir.
Do you need them all?
No, all you need them. You cannot compute them. But in my work that I'm going to show you, I don't need them all. I need only a few of them, because I'm not going to solve the direct problem. Let's say I am going to solve an inverse problem where you need only a few of them. Also, you'll see. As I said, that this problem is not very well discussed in literature. In fact, there are quite a few numerical linear algebra books now. None of the books talks about this problem because they're not much known. But because of my own interest, and I put 2 chapters in my own book, Numerical Linear Algebra and Application. This second edition was published by Simon in 2010. And there is a review paper of Biswa and Meyerbergen. It's a good survey of that problem. Okay, let me now come to the control part. Now, suppose you apply a force to the structure of the form BUT, where B is a fixed matrix called control matrix. You don't have to know much control theory, just and E of T is called control vector. This is a vector. Control vector is something at your disposal. You can freely choose that vector. Okay, that's called its control vector. You can control it. Okay, so suppose we decide to choose that vector U of T in the form U of T equal to Ft x dot t plus gt x t, where F and G are 2 unknown matrices. They are called feedback control matrix. Now, with this choice of U of T, if we just substitute that U of T in this equation, what you get after substitution, I'm sorry, there's a typo here. Just forget about this lambda square. There is no lambda square here. So you get what is called closed loop system. Now, again, this is the dynamics of these closed systems are governed by the eigenvalues and eigenvectors of this closed loop quadratic matrix pencil. In these pencils, everything is known except F and G, because B is the control matrix given to you. F and G are unknown. And as you all know, the resonance is caused only by few bad eigenvalues. What happens when a one or more natural frequency becomes very close to the external frequency, that means frequency of the external force, like earthquake or gusty wind or the weights of the human bodies, then the resonance occurs. So to control the resonance, all you need to control only few those bad eigenvalues. Okay, natural frequency corresponding to eigenvalues. So the problem here will be how do you choose these two matrices B and G, I'm sorry, F and G, in such a way that those resonant eigenvalues will be quickly replaced by suitably chosen eigenvalues by the engineers who have some idea, because of the long time experience, they know what are the good eigenvalues to be chosen. So those few resonant eigenvalues will be quickly replaced by suitably chosen eigenvalues by the engineers, while leaving the remaining large number of eigenvalues and eigenvectors unchanged, or at least they should not spill over to the region of the resonance. You understand the problem?
So you're going to fix the lambdas and find the F and C?
Lambda corresponds to an eigenvalue.
Yeah.
So once you know what are the bad eigenvalues, you want to replace them by some suitably chosen good ones. On the other hand, the remaining ones which have not been computed and the corresponding eigenvectors, you don't want to, they are supposed to be good, so you don't want to perturb them. You want to keep them as they are in their own places. Or at least you should do something so that they don't get spilled into the region of the resonance.
Because you said the F and C are not.
Yeah, that's what my problem is. How do you choose that this will happen? That's the problem. That's the control problem. And this F and G have to be computed in a very, very fast way for the algorithm to be effective. Okay, is that clear what I'm saying? Yes.
So after getting F and G's, it's to find important eigenvalues is easy, or still is a hard step to do?
Sorry, I didn't get you.
Like you said before, first we have to get this F and G's, right?
Yeah, you have to get, well, not any F and G. You have to get F and G in such a way that the identified bad eigenvalues which cause resonance will be replaced by good ones. Okay. And normally, from engineering experience, one has seen that the first few eigenvalues are bad. Okay. Okay, so mathematically, the problem will be something like this. Okay, the problem will be find the feedback matrix F and G, as I said, such the few resonant eigenvalues. Call them lambda 1 through lambda p, where p is much less than 2n, of course, small number of eigenvalues. So let me tell you what is p. The state of the art is p is 20. No matter how big the structure is, even the companies who try to solve this problem, NASA, Boeing, they all work with first few 20 eigenvalues or so, and first 20 eigenvalues or so. So if the first p eigenvalues are replaced by suitably chosen ones, say mu1 through mu p, while the remaining 2n minus p eigenvalues and eigenvectors will remain unchanged. This last phenomenon is called the no spillover phenomena in engineering literature. So this is how the mathematical problem is. Okay. So the problem is how to solve such a problem. Of course, always approximate, always all numerical solutions are approximate solutions. They can be different, yeah, they can be little perturbed. Yeah, you are right. They can be little perturbed. While any eigenvalue computations, you always put some perturbations. That's why I'm coming to that topic. You have a very good question, because you have to do in such a way that the eigenvalues of the closed loop pencil do not get perturbed very, very much. That's a very important property to be kept. I'm coming to that. That is a very good question, actually. Okay. Now, this is the basic problem, how to find FNG, that this will happen. However, in practice, we like to have some more properties from FNG. Any FNG will not be a good one. The properties you like to see, the practical properties you like to see, that they have norms as small as possible. Why? Because the small norms means less energy. That results into something called economic design. Okay. And the most importantly, as he was pointing out, most importantly, you like to construct the FNG, the compute FNG, in such a way that the closed loop eigenvalues, after you do everything, the closed loop eigenvalues will be as insensible as possible to small perturbations of the data. This is called the robust property, because you don't want to do too much perturbations, so eigenvalues will be all perturbed. So this is the most important part. The FNG should be computed in such a way that they have norms as much as possible, and the eigenvalues of the closed loop pencil will be as insensitive as possible to small perturbations of the data, because eigenvalues are known to be very, very ill-conditioned in practice. The small perturbation of data can cause the big changes in the eigenvalues. You don't want to do that. And as you can see, these two problems give rise to some very difficult optimization problem. And I was talking to one of the world experts in optimization yesterday to get some of his opinions. And
You're still waiting.
No, it's so hard. We have been just able to make little dent, but far from the solution, because yes, sir.
The complexity grows with the P and N, or
Yes.
both? The number of fixed eigenvalues.
Yeah.
Which one is more?
Well, P is in a small anywhere, so N is the important thing.
But you said there's a reason why P is small.
Because we cannot compute more than that, Yeah. Now the complexity for this optimization problem is that the second part, gives us a nonlinear, non-convex optimization problem. And as you know, that this is a very difficult problem. Even the optimization experts don't have any much working algorithms to solve this problem in a good way. So that's where the complexity is. We'll look into the problem. I don't have a solution, but I can show you the problem. I have some solution, but those are just.
Sorry, I have a question.
Yeah.
Like, what does it mean in practice that these eigenvalues are insensitive? Like we are always taking the same control action?
No. The control matrices have to be computed in such a way that you see when you have a F and G, right?
Yeah.
When you put the F and G in the system, you get a closed loop system, right? You get a set of eigenvalues, okay, of the system. Those eigenvalues should be insensitive.
Yeah.
That's what I'm saying.
Yeah,
so it depends upon F and G or what you compute.
Or what I mean, in practice, what happens if the eigenvalues are sensitive to the data? Like, what will happen?
Then you see that's what he was trying to say. You see that what happens that you want to keep the large number of eigenvalues, eigenvectors unchanged, right?
Yes.
So if they become perturbed, everything will be lost. because those eigenvalues will be bad again to work with. They have been identified to good one, you don't want to perturb them.
Maybe that's another response to that. Yesterday he was mentioning that of those original matrices, the mass, the stiffness, and the damping, the M, C, and K. So, if correct me if I'm wrong, the M and the K can be well estimated, but the damping matrix
Is unknown. Is
the engineers don't know how to measure.
Right? How to estimate that?
They have just a rough estimate of the damping matrix, but the real structure may have a different matrix. So if you're controlling for one system and in fact your building has a completely different damping, maybe the dynamics will be very different. So if you get insensitiveness to this knowledge of the damping matrix, is a good thing, because that means that you have a robust design that works for many matrices. That's the idea.
Yeah, actually, that as you said, since we don't know what damping is, ideally, any algorithm to compute F and G should be such that it should be independent of damping. Though, damping is there, right? But we don't know what it is. So we should not explicitly have an expression of F and G containing the damping. Okay, and I have a solution. I can show you that. That is exactly happening. Okay. So how do you solve such a problem? Well, what happened? The standard thing to do, as I said before, that you have a quadratic control problem. Okay, you again, like eigenvalue problem, you transform the problem to a first order state-space system problem, they call it. X dot equal to X plus BU, the typical control system. Now, if you do that, then the problem is that, again, as I said, you will lose all the structures of the matrices M, C, and K. Okay, but if you can do that, of course, it's very easy. Everything becomes very, very good, because there are beautiful techniques, excellent techniques numerical techniques to solve the first order problem of this type. We call it in control theory called pole assignment problem, or something called partial pole assignment problem. There are beautiful techniques to solve this. It's a classical problem for first order system. And in fact, I have a control book, as you was mentioning, and I have 2 chapters devoted to that problem. But as I said, because of the computational difficulties, practical difficulties, the problem should not be solved by transforming the problem to a first order problem. It will be solved in the quadratic setting itself. Okay. Though if you look into any vibration engineering book, nobody talks about the quadratic problem, because they don't know how to solve it. Period. They routinely teach the students, okay, you have a problem, transform the first order problem, solve it. We have good techniques to do that. Here it goes. But they just put all the difficulties. They sometimes know what the difficulties are, put under the rug. That type of thing. It's true. I have talked to many vibration engineers, and I have many friends, and their books say, they said, well, that's what it is. Okay. Oh, what I'm doing? I'm going back. Why? Okay. So let me tell you. Let me first show you a solution to the basic problem. Just I'm not talking about optimization part yet. Just a solution to the basic problem. How to compute F and G such that a small number of eigenvalues which are identified as bad ones will be replaced by the suitably chosen good ones, and the remaining large numbers of eigenvalues and eigenvectors will remain unchanged. The problem would be solved in a computational, in second order setting itself, in quadratic setting itself, by knowing only few eigenvalues and eigenvectors that need to be replaced. That's it. And the algorithm, as you can see, will be really fast algorithm because computation requirement is minimum. You cannot just think a better. I mean, I should not say that. You cannot think that is as fast as possible. I should not talk much about my own thing. Okay, so the solution comes in two parts. The first part, the no spillover part. That means to guarantee that the large number of eigenvalues and eigenvectors will remain unchanged. That part is the most difficult part to have. And that part, you have to do it. You have to prove some mathematical result to demonstrate that part. Because in practice, you don't have the luxury of recomputing all the eigenvalues and eigenvectors after you put the feedback to see whether changes have occurred or not. Because there is no way you can compute all the eigenvalues and eigenvectors. So that part has to be proved mathematically. And once you have some mathematical result, then you have peace of mind. At least, theoretically, they will remain unchanged. In practice, they can change a little bit, but that will not be, that will be quite effective. That will be acceptable. Okay. So that part is done in the first part. I mean, in this first in stage one of the solution that is done. Here I saw that if you compute your F and G in this way, where M is the mass matrix, lambda 1 is a diagonal matrix of the P eigenvalue lambda 1 through lambda P, which are known to you. Okay. And so if you choose your F and G in this way, and X1 is the corresponding eigenvector matrix. Eigenvector matrix is corresponding to the matrix lambda 1. Okay. So if you choose your matrix F and G in this way, then I can show mathematically that for every choice of this matrix phi, I don't know, you call it phi here or phi, how do you call it? Phi. The reason I'm asking, I had one problem. I was giving a lecture in Athens Technical University. and a student not student, a junior colleague, he stood up and said, "Professor, you are abusing your language." Because I was used to call phi, mu, nu, and they said, "Why? What happened?" He said that it's not phi, it's phi. It's not mu, it's me. It's not nu, it's me. I said, "I'm sorry." So since then, I have changed. But still my students say, "What is phi?" I said, "It's not phi, it's pi." Anyway, so for every choice of this matrix phi, I can show that F and G are such that there will be no spillover. And this is the mathematical proof to do that. Now this is a very, very beautiful result, because now we have a free parametric matrix phi. Now the question will be then, how do you choose that parametric matrix phi in such a way that the P eigenvalue lambda 1 through lambda P will be replaced by mu 1 through mu P? Because any choice of P will preserve the eigenvalues anyway. So now how do you choose that matrix P? So the first part of the problem is assignment part will be solved. Okay. So there I can have a little algorithm. The algorithm say, if you choose the P by solving this P by P linear system, where the matrix G comes from a solution of a matrix equation called Sylvester's matrix equation. Many of you know about the Lyapunov matrix equation. This comes to the Lyapunov stability theory. The form X plus X equal to C. This is a very special case of that. It's called Sylvester's matrix equation. But this Sylvester's matrix equation is almost trivial to solve, because here lambda 1, I'm sorry, lambda 1 prime is the diagonal matrix of the eigenvalue mu1 through mu p. Okay, so as you can see, the matrices of the Sylvester matrix equation are diagonal in nature, so they are almost trivial to solve. This equation is trivial to solve. So once you gamma, and here is an arbitrary, again we have a parametric matrix gamma. So any arbitrary gamma, if we solve this matrix equation first, get your z, then solve a small p is very small linear system, then the matrix phi you get, that will do your job, and that solves the whole problem. It sounds very simple, however, believe me, it was very, very hard to prove. The first part was the most difficult part, and it was the originally proof. This result was proved in 1997, something like that. And I got together with some vibration engineer at University of Adelaide in Australia, and some computer scientists. We were working on this problem. I was visiting them. There is something, we needed something called an orthogonality conditions for the quadratic matrix expansion, which did not exist. That was the bottleneck. We were just banging our head, nothing came out. One day, I lost my sleep. So I got up in the morning and I got the solution. Got up means I could not sleep the whole night. And I called my colleagues that I have a solution. He said, we have a solution too. And then we converged. So it's very interesting. But the bottom line is not very easy to solve, but very easy to prove the part that we're happy that we did that. And now this is routinely used by everybody. There are hundreds of papers have been written now, okay, on different sophistication of this, but this is the basic thing. Yes, sir. Gamma is an arbitrary matrix. It's a parametric matrix. So, no, this is what you can. That's why I'm coming. That gamma is a parametric matrix. It is at your choice. Okay. Now, there is another beautiful thing about this algorithm, that we have the parametric matrix gamma. We need to have a parametric algorithm, because we can take advantage of the parametric matrix gamma to solve our optimization problem. Because now we'll ask ourselves, how do we choose that gamma so that the corresponding optimization problem, the two problems I talk about, can be solved? If I did not have any freedom, then that was the end. But now I have a freedom. Understand what I'm saying? Yeah, for some gamma, we are hoping for some gamma, the corresponding optimization problem will be solved. That's what we're hoping. Okay, so let me go to optimization problem now, at least to the statement, not to the solution. Okay, well, the first part of the problem, there's an interesting thing that the robustness part, that second part, the minimizing the condition number of the eigenvector matrix, the insensitivity of the closed loop eigenvalues, that amounts to be minimizing the condition number of the eigenvector matrix. Now, this part, and I gave it to a student of mine, and he banged his head, could not solve the original problem. So he came up with an idea. He said, okay, I cannot solve the problem. I cannot find the right y. Y means the eigenvector matrix, closed loop eigenvector matrix. What I can do, I can compute an eigenvector matrix such that that matrix Y is as close as possible to an orthogonal matrix. That means this Frobenius norm of I minus Y Hermitian Y squared will be as small as possible. The reason he said that orthogonal matrix is known to be very well conditioned. The condition number is 1. So if you can have a matrix which is as close as to orthogonal matrix, probably that matrix should be very insensitive in perturbations. I mean, the eigenvalue will be insensitive to perturbations. That means that matrix should have small condition number. That was the idea. It's a heuristic idea. It worked. It worked means we had some numerical examples to show that it worked. However, as a mathematician, I was not happy because this real problem was not solved. Then I was telling him the story. I got together with a very bright Chinese mathematician. He was a student of a friend of mine. Oh God. Okay, and then we tried to combine these two problems as in one problem. So that means we have now a one objective function for both the problems. As you can see, the first one, okay, I forgot to tell you, the minimizing the condition number of the eigenvector matrix Y is mathematically equivalent to minimizing the square of the Frobenius norm plus the Frobenius norm of the inverse of Y. These two things are mathematically equivalent. So the first part you can see of this objective function is, first part corresponds to the robustness part, minimizing the condition number. And the second part, of course, corresponds to the norm minimization. Okay. And alpha is a parameter between 0 and 1. So if alpha is 1, then we have the robust problem. If alpha is 0, then we have the other problem. Okay. So it's a combination. Alpha is 0 is norm minimization, alpha is 1, we have the condition number minimization problem. So the problem is an unconstrained nonlinear optimization problem. Okay, it's non-convex also, right? So the problem is how to solve such a hard problem. Okay. Now
Here, the Y, the F, and the G depend on the matrix gamma. Gamma is what you're choosing.
Right. They're all parameterized by gamma.
And you minimize over gamma.
Right.
Subject to this constraint you wrote on the previous slide.
Oh, there is no constraint.
No, but the expressions for Y, F, and G are given in the previous slide.
Right. Let me tell you one more difficulty here. So we can mathematically have an expression for the eigenvector matrix Y, and this is how the eigenvector matrix Y look like. You see, the y1 and lambda 1 prime are known to me, but this part is completely unknown. This part has not been computed. Okay, because x2 is the eigenvector matrix corresponding to the eigenvalue lambda p plus 1 through lambda 2n. And lambda 2 is the corresponding eigenvector matrix. That part is completely unknown. Okay, so the problem is how do you minimize the condition number of this matrix Y only only a small part of that matrix is known. The rest is unknown. So the problem was, first problem, of course, how to compute the gradient formula. Okay, computable gradient formula. Well, for that, what we tried to do, we showed that the objective function J can be written into 3 parts. And where J1 and J2 will depend on the first part, known part, and J3 will be independent. So that part can be neglected for computing the gradient formula. Okay, and after a lot of hard, mathematical manipulations, we call it, we were able to show that we were able to show that the gradient formula can be computed, assuming, I should not say, I should be honest, assuming some part of the unknown is known to us. So what we know, we need to know, actually, we need an a priori estimate of the upper bound of the reciprocal of the smallest singular values of x2 hat the second part. Okay, so if you happen to know that somehow, okay, then you can compute the gradient formula. That's what we were able to prove. Okay, it's quite involved. So we had that, we computed 5 more minutes. 10 more minutes. Okay, I'm okay. Yeah, I wish I could spend some more time here, but there is already next time, right?
Yep.
Right, next time.
Sure.
Okay. So what happened? We ran some. I don't know. I somehow missed that beautiful graph. I mean, beautiful figure that you have. I don't know what happened to it. Somehow it didn't come. Okay, but what happened? We ran some examples with practical live data from NASA. I tell you something. I used to be a consultant of Boeing company, but then I had to split from them because they are so secretive of what they do. You know, they even did not trust me with the data, and they were using my algorithms without telling me what they're doing. So I just divorced them, and but I have some good friends at NASA, so I got some real life data. Not real life data. They don't give me real data. Simulated data. Okay. So I got some simulated data, ran some examples, and I'm sorry, I somehow this I'm missing that slide. So with that, what we did, we computed the gradient formula, fit that into some optimization software. I don't know what software we use. I forgot. What are the well-known software that you use? Anyway, I forgot. I'll tell you later. Anyway, so the result was that what happened. We packed up the K matrix. I just said that's the only one that because M is accurately known, C is unknown. Oh, by the way, when you looked into my algorithm, did you look that there is no C there? The eigenvalue and eigenvectors, of course, were computed from a structure. So there is C there implicitly, but in the algorithm itself, we didn't have a C. That's one of the beautiful things I forgot to mention. Okay, and the algorithm was able to exploit the structures of FNG. Also, baby, I mean, if you're, I'm sorry, not a FNG, structures of M, C, and K. Okay, so that was a good algorithm. That's what I want to say. So what happened? We did some small perturbation to the matrix K. Okay, and then we measured the system response. What we saw that both feedback norms and eigenvalue conditioning were substantially reduced. What's the word reduced? They are not minimum. Okay. Because we don't have the global solution. We don't know what the minimum is. Okay, they are substantially reduced. And the system responses remain unchanged with small perturbation of the state matrix K and successfully tends to the steady state, showing that the scheme was kind of robust. But that's the state of the art of the problem. Okay, we have not been able to do any further. We don't know the solution is global. We don't know what else to do. Nobody else have been able to help us so far. I talked to Roberto yesterday about this thing. Hopefully we'll have some ideas, we'll see. Okay, I have 5 more minutes, right? 5 more minutes. I'm bargaining with you.
Well, they need the room like in 5, so.
Okay. I want to talk to a few words about the other problem. So can I go for 5 more minutes or just stop here?
I mean, depends on if there are people waiting for us.
Let me see.
Okay, don't worry. Don't lose time.
Nobody's here.
Let me take a pic.
But my taxi is waiting, right? Maybe I stop here.
Huh?
Maybe I stop here. You know.
Yeah, maybe.
Yeah, so maybe. Okay, I look forward to talking to you about the other problem and next time. Okay, thank you for your patience. I really appreciate your patience.
Thank you.
And it's, as I said, it was a pleasure for me to be here. Thank you.